All right, so video 4.2.4, and you made it to the last problem, to example 7. So give yourself a pat on the back. It's not easy. There's a lot of problems. So let's go ahead and tackle this very last problem. So we have a 1 liter solution where we have 0.1 moles of, again, my vinegar and 0.05 moles of my sodium acetate combined. So the first thing you need to notice are that these are very similar. And how are they related? Well, this one's the acid, and this one's the conjugate base. The sodium doesn't really matter. This salt's going to break apart. So the sodium acetate here is just a source of acetate. So really, this is just C2H3O2 minus, and you have some spectator sodiums out there like floating around. But we don't even really pay attention to those. So we have your acid, and we have that acid's conjugate base. So we have a weak acid plus conjugate base. Now, this type of problem, when you have a weak acid and its conjugate base, or a weak base and its conjugate acid, is a buffer system. So this is a buffer. And this problem is unique because there's actually 2 ways to go about solving it. So I'm going to show you the first way, then I'll show you the second way. So first way, again, we're going to use our icebox and our Ka. So we'll use icebox or ice table and Ka. Okay, so the first thing we always have to do, of course, is to write our equation. We're going to write our equation for our acid here, because our acid's going to contribute the most. So pick your acid, not the conjugate, to write the equation for, because the conjugate will already show up on the other side anyway. So HC2H3O2, double-sided arrow because it's weak, H plus acetate. You guys are really going to know acetate and vinegar by the time we're done. Okay, so how much of this did we start with? How much of our vinegar? 0.100 moles. No hydrogen ions in solution at all. There's no other acid or anything contributing to that. But we do have a source of our acetate, and that's this guy right here. We have 0.05 moles of our acetate. So this is another common ion type problem, just like the last one. Minus x plus x plus x. It's finishing out our table. Okay, there's our ice table. Now we're going to go ahead and use our Ka. And we know, and I'm sure you've probably memorized the Ka at this point, but if you haven't, your Ka equals 1.8 times 10 to the negative 5 for vinegar. So Ka equals your products over reactants, so H plus, and your acetate over your acetic acid, and rewriting all this, your H plus is x. And now this, I'm going to again ignore this x, and I'm going to ignore this x, because we're going to assume they're very, very small, which they are in relation to these numbers here, because this is a very weak acid. So we have 0.50 here, and ignoring the x, over 0.100, and again, ignoring that x because it's really small, equals your Ka, which is 1.8 times 10 to the negative 5. So x is equal to 3.6 times 10 to the negative 5. Okay, at this point, I would like you to pause this video and find all of the concentrations for all of the species here, and I want you to find OH concentration, H plus concentration, pH, POH, and percent dissociation, just like we've been doing for the other problems. Go ahead. Alright, so coming back, let's go ahead and solve all of these. I'm going to write my line so I stay separated. First, the concentration of HC2, H3O2, equals 0.100 minus x, so minus 3.6, times 10 to the negative 5 equals, no surprise here, 0.100 molar still. My concentration of hydrogen ions is just x. So that's 3.6 times 10 to the negative 5. My concentration of my acetate equals 0.050 plus x, so my x is 3.6 times 10 to the negative 5, which, again, no surprise, is still equal to 0.050 molar, and that's why we ignored that x in the first place. It doesn't make a difference. Okay, so now I have all of these concentrations. I can easily find my pH because I have my H+. pH equals negative log of my H+ concentration, 3.6 times 10 to the negative 5, which is 4.44. POH equals 14 minus 4.44. And so your POH is 9.56. So that's good. My pH and my POH are both in the acidic ranges there. Concentration of hydroxide equals 10 to the negative POH equals 10 to the negative 9.56. And that gives me 2.8 times 10 to the negative 10 molar. And then finally, my percent dissociation equals my x, so 3.6 times 10 to the negative 5 over my initial 0.100 times 100, and that gives me 0.036% dissociated. Okay, that's the first way to do this problem. So just like before, there is another way to do it. So I'm going to show you method number 2. Because this is a buffer, you can use something called the Henderson-Hasselbalch equation, the HH equation for buffer solutions. It only works with buffers here. So that's actually listed on the back of your periodic table. So I'm going to show you how to use it. So method number 2. Use the Henderson-Hasselbalch. We just call it HH. People abbreviate it HH for short, and you can see why. Equation. And only for buffer solutions. And it saves you a ton of time. So here's the Henderson-Hasselbalch equation. So pH equals pKa plus log of the concentration of A minus, so that's going to be your conjugate base, over your HA, which is your acid. So we'll go ahead and label that. This is the acid. This is the conjugate base. And so this is for if you have an acid and its conjugate base. Or you can modify this equation. POH equals pKb plus log BH plus over B. So this is the conjugate acid, and this is your base. Conjugate acid, here's your base. Okay. So we are going to use this equation right here because we have a pH, because we have a conjugate base and an acid. We have acetic acid and we have acetate. So let's go ahead and plug everything in. So pH equals, now pKa, remember when we were talking about pH, what that P stands for, P means negative log. So all you have to do is take the negative log of the Ka. So pKa, so let's write that, is negative log of the Ka. Okay, so our negative log of Ka, and so just writing that out, I had negative log of 1.8 times 10 to the negative 5. That, of course, is our Ka from above. Okay, so that's the pKa part, plus log of the concentration of your conjugate base. So looking up above, concentration of the conjugate base is 0.05. The conjugate, or I'm sorry, and then the concentration of the acid is 0.1. So plus log of 0.050 over concentration of the acid is 0.100. So that's all you needed. So plugging all of that in, you get 4.44 as your pH. Now this was literally all you had to do to solve this problem. Just this part right here, if you knew the Henderson-Hasselbalch equation. Now from the pH you can find everything else. So I'm not going to do that again because we just did it above. So can find everything from pH. So from pH you can get the concentration of H+. You can also get POH. From POH you can get the concentration of hydroxide ions, so on and so forth. So this is another way to do problems with buffer systems. And remember, this only works with buffers. You can pick either way, whichever way you like on a test. Alright, that is it for section 4.2's notes. Thanks for hanging in there through all those problems. Have a great day.